Share. Is it okay now, Gabi? Yeah,
Yes, I
good.
actually
Thank you.
did it. I just forgot that I did it already. I was prepared.
Good. All right. So, welcome back in here. And now we're going to talk about something important. Not that we haven't spoken about important things so far, but we'll talk about something also important. Let's put it that way. Just looking at my thing to see my. Yes, that's good. Signal backgrounds and noise. Let's see. So we have been, I've spoken a little bit about the crosstalk between, that's basically the contrast in image. And you understand that the final resolution that we get in our image depends on the objective that we're using and the wavelength, depends on the how good our sample is, how close it is to a perfect sample, and also on the contrast. And the contrast is influenced by the the noise and the background, and therefore we're going to talk about this now. So what is this? Oops, sorry, my mouse is here. Here. So the signal to noise or signal to background ratios are often abbreviated as SNR and SBR. Unfortunately, most people mix them up, and you will see now that it's not the same thing. So most people talk about this SNR, signal to noise ratio, when they really mean the signal to background ratio. So I hope that after this course and after this lecture, you will not mix them up, because they are not the same thing at all, and therefore we have to do different things about them. So why do we care about the background? Well, you can see in here we have this little ball in the field, and we're trying to hit the ball in the wrong place. If your name is Sylvie when you're playing golf, and you don't know where the ball is, you have to find the ball. How do we find the ball? We are looking for this. This is our interesting signal, and then you have lots of stuff that is hindering us from finding our ball. The background is the grass. The background does not change from one image to the next. It is real fluorescence. It's only fluorescence we do not want, but it is fluorescent. So if you take 3 images, unfortunately, it's not going to make your background disappear. The noise, however, is something that changes randomly between 2 consecutive images. So I've had several people now coming to me, and for some of you, I have demonstrated the noise, and I think you have had as an assignment to take a very short time lapse of your sample, and we're going to use this to look at the noise in our images. So the noise changes and it's random, whereas the background doesn't change. So the noise comes from the imaging process. As I've shown you the sensors, we have a whole process, and some of this process of amplifying the electrons, reading the voltage, and digitalizing the image, some of this unfortunately creates noise in the image. So this comes from the imaging process, and it's not real fluorescence, even though it looks like small dots all over our image. It's not real fluorescence. So we often call background everything in the image that we wish were not there. For example, the offset of the detector, so we're going to see what that is. If your antibody sticks as specifically to everything, we say, this is background. So if we have autofluorescence, it's background. If we have fluorescence in the mounting medium, it's background, etc., etc. Everything is background. But actually knowing where your background comes from is a great help to try to tackle it, because the solution to all of this is completely different. So you need to know where the background comes from to be able to eliminate it. So lowering the background and the noise is as powerful as increasing the signal when it comes to improving the signal to noise ratio or the signal to background ratio. You can move the noise up or decrease the background and noise. Okay, it has the same effect. So everybody tends to think, oh, I'm going to push the lasers, so I increase my signal, and actually we forget that we need to work on the background and the noise as well. So cut the grass so that you can find the little ball. Here is a nice zebrafish embryo. They are autofluorescent. So we get, oh, interesting, these cells are fluorescent. This is our signal. This is what we would like. Unfortunately, there's a lot of autofluorescence around, and that we say, oh, that is a boring background. We also have this yolk that is superfluorescent. That is a very boring background. So you can see that the background can even be stronger than the signal in some cases. It's basically the background is fluorescence, but it's the stuff you do not want. So here we have a sort of a modeling of background signal to background ratio. So here the signal, what is the signal? It is basically the intensity in the pixel of interest, the pixel that you're interested in. That is your signal. The background is everything else. So the intensity outside the pixels of interest is the background. So that would be the black thing there around. So in these images, we have the background is always the same. So it's set to 100, but the signal increases from one image to the next. And therefore, our signal to background ratio starts from 1.5 and it ends at 50 because we have increased the signal. So one way to increase the signal to background ratio is to increase the signal. So what is a good signal to background ratio? There is no rule. It's the same thing as everything else. It all depends on your scientific question. So whichever signal to background ratio allows you to extract a reliable answer to your scientific question is best, right? So if you have a very low signal to background ratio, but you can get your reliable answer, fine, you don't need to bother. It's the same as everything else. I'm giving you the gold standard, and then you have to position yourself compared to this gold standard based on your scientific question and how reliable your answers are. So it depends on the scientific question. It depends also on the technique used to image. So the signal to background ratio is going to be completely different if you use a wide field system or if you use a system that has an optical section. And it depends, all you want is to acquire meaningful and reliable data. And that is not the same thing as acquiring beautiful images. So you know that meaningful and reliable data, this is what we do most of the time, and that's real hardcore science. Beautiful images, this is what we do very seldom to get the image into a publication. Okay, so beautiful images, forget it. But our brain is geared towards beauty. So you have to rely on numbers and not on your eyes. So how can we increase the signal then? To improve the signal to background ratio, we can push the signal. How do we increase the signal in images? Well, if we have fixed samples, we can push the illumination power. So the lamp or the laser or something. We can also use longer exposure time. So we integrate more photons before we clean the camera, or slower scan speed. So this is the pixel dwell time. So we can have a bit longer pixel dwell time. So pixel dwell time, again, is a little bit the exposure time per pixel on a single point confocal. So we can have longer pixel dwell time or exposure time to integrate more photons so that we get more like a brighter pixel. We can also use averaging. We're going to see this. We can bin the camera because, as you know, we can, when we bin the camera, we have if we bin 2 by 2, 4 camera pixels will make 1 pixel in the image. And therefore, there's a much bigger area that the photons can fall onto, and we get a brighter image. So the signal is increasing by binning the camera. We can also open the pinhole on a single point confocal. We can open the pinhole and then we get more photons in, but we have a smaller optical section. So when we use fixed samples, we just need to be careful with bleaching. With all samples, actually, we need to be careful with bleaching and phototoxicity for live samples during a Z stack. And that is because of the shape of the illumination that we illuminate above and below the planes, as well as at the plane of interest. So we have bleaching every Z stack, we bleach the whole volume for each Z. Okay, so the only machines that do not do that are a light sheet system and a multiphoton system. Everything else bleaches above and below the plane for each Z plane. And of course, if your sample needs to be reimaged later, you have to be careful also with not bleaching it. But if you don't care about this, if you don't care, if you don't think that you have a problem with bleaching or you don't need to reimage your sample later, just blast the thing. Put a higher laser. I know so many people who just use 1% of the laser, whatever happens. No, there's a reason why there is a slider. We can move them up and down. So put a lot of light and dare to bleach every single photon out of your sample while you're getting the image so that you get good data. And then you throw away your sample afterwards anyway, okay? So push that laser button. So this is a great way to increase the signal. Now, if we have live samples, of course, it's different. We need to have very gentle imaging parameters. And these parameters need to preserve the biology to be observed. This is the key, is that you do not want the imaging process to influence the biology that you are observing. Okay, and I think you've watched the video about imaging live samples, and you have seen that we have to do lots of controls to make sure that our imaging does not influence the biology that we want to observe. And then we want to have the minimum light exposure to have the minimum phototoxicity. Minimum light exposure required to be able to reliably analyze the image, so acquire reliable data. Okay, so we put just enough, and forget about beautiful images. We just want reliable data. And for any sample, fixed or live, we need to have absolutely no saturation and no underexposure in the area of interest. Okay, so we're going to talk again about saturation and exposure today. So this is the way to increase the signal, but we need to be careful with that. And we always need to test the whole pipeline from sample preparation to image analysis so that we know if our imaging setup is actually working for the image analysis. So do not spend, please, time acquiring lots of images without testing the image analysis pipeline. We need to go all the way to the end. So now that we know how to increase the signal, here we can see in this little simulation what we have instead of the signal changing. Now the signal is always at 500, but our background is increasing. And as you can see in this low signal to background ratio image, only 2 here, whereas here we had 500, we have a low contrast. And if we have a low contrast, it is much harder to analyze the image. Okay, so the contrast is very important. So what can we do for the background? Well, the background can come from different imaging conditions. The background can come from different sources. It can come from the imaging conditions. It can come from the sample. So we're going to look at this now. So the background that comes from the sample, it could be, for example, that you have live cells and you have a cell culture medium that is fluorescent. It's quite common. I think Gabby spoke about it also in the video about live sample imaging. It's very common that the cell culture mediums, they are quite fluorescent in the green channel. So maybe you can choose by simply changing the channel you're imaging, you can get rid of that background, or you have to change the culture medium. As we have seen several times in when you guys come to me with the student imaging challenge workshop, the mounting medium can be fluorescent. And clearly, if you have this type, so you can see it when you have a bubble. If you image inside the bubble with your fluorophores, if you see the bubble, if you're focused, actually, you can focus on this bubble with transmitted light. And then you take an image in fluorescence. If you see this, it means your mounting medium is very fluorescent. If your mounting medium is not fluorescent, that you do not see a difference in intensity between inside the bubble and outside the bubble. Okay, so here is another example of fluorescent mounting medium. So another source of background that comes from the sample can be the autofluorescence of the tissue. So it can be also the cell culture medium and the mounting medium. The autofluorescence of the tissue can be amazingly specific. It looks very specific in some specific cells, but it anyway comes from the tissue. So remember to always image at least once your sample without labeling it so that you are aware of in which channel you have autofluorescence. Also immunostaining with aspecific binding. So all these dots that you have all over the place, outside the place where you expect your antibody to stick, this is also background, and it's aspecific binding. So that is also background coming from the sample. So you know that to reduce this, you reduce the primary so that your antibody doesn't stick everywhere. And so we have given you some tips here in the sample preparation and the live cell imaging lectures about how to decrease the background from samples. And the background can also come from the imaging condition. And one thing is stray light. So for example, we have this image. Is this a specific signal? Well, let's have a look at this little time lapse of the thing. Wow, what's going on in there? Right? It looks very much that we have either signal or no signal, a signal turning on and off, where actually what it is a desktop lamp near the microscope that was either pointed towards or away from the microscope. So this is stray light. This is definitely something we do not want, and it's quite easy to deal with. Just turn off the light. And this is visible in a system that does not have optical sectioning, because clearly on a system that does optical sectioning, you're going to throw away the light that comes from the outer focal plane, and the light that is on the desktop is out of your focal plane, so this light will be thrown away. But here we have a wide field system with an EM CCD camera, so very sensitive camera, and this objective, we are seeing the desktop lamp. So turn on the overhead lamp when imaging with a microscope without a pinhole. If we think about the background from imaging conditions, it can be also the sensor offset. So we're talking now about single point confocal. And let's have a look. So we can have, you know, that the single point confocal, we have detectors, and otherwise we have cameras. And so if we talk about the single point confocal now, the sensor offset on the when you acquire an image on the single point confocal, you can change the gain. You can sometimes also change the offset. And now I say sometimes because the newer type of microscopes do not have an offset, because it is set automatically in a different way nowadays. But for the a little bit older single point confocal, you're going to have gain and offset. So even a new microscope, you will have gain, right? So the gain is the amplification level. Remember this stuff about we collect photons and then we transform them into electrons, and we amplify, and then we read the voltage, and then we convert this to a digital signal. So this amplification, this is the gain. That's what you do. So how bright the sample is going, how bright the image is going to be. The offset is the lower level of sensitivity. So how dim, so what is the lower level of light that we can detect with the sensor? This is what the offset is, okay? So in this image, we have color-coded the saturated pixels in red and the underexposed pixels in blue. So you can see here we have this saturation underexposure mask on in this image. And what you can see is that we have saturated pixels, they're red, and that we have really a solid blue background like this. And we will see the consequences of doing something like this. So here we have a low detector offset. It means you will get a very nice, once you remove this mask, the background will be very black. Oh, lovely. But the problem is the offset is too low. So what happens if the offset is too low here? We're going to get a solid black in the background. There will be no nuances no little variation in the background. And so the detector is simply unable, in the way if you set the offset too low, you are preventing the detector from detecting weak signals. So not only here, but also inside the cells. So don't have that. We do not want to have any underexposure in our images. This cannot be fixed after acquisition. You're just preventing the detector from acquiring. If in another way the offset is too high, what we will have when we remove this blue color mask is that the background is going to be a little bit gray. Okay, it's better to have the background gray than completely underexposed like this. Because if you have the background gray anyway, all the dim signals are detected, so you're not missing anything. And that can be fixed afterwards. You can do some background subtraction afterwards. So it's better to have an offset too high than too low. So set the offset level to just above the level where you get a few of these blue pixels that are color coded in, just above that, and that is the good level offset. So we do not want a completely black background, and we we want a black background, but no underexposure. So we do not want, when you put the color mask on, we do not want this to be blue. Always keep the saturation and underexposure mask on when you change your settings so that you can detect if you're going too low or not. And set the detector to have no saturation at all, so no red, and no underexposure, no blue in the area of interest. And again, on modern detectors, in modern single point confocals, you do not have this offset because it is calculated automatically by the electronics, so you don't need to bother anymore. But people who have a little bit older, you know that you have offset and gain, and this is the way to set your offset so that you have no blue in the background. So now if we are talking about cameras instead, we also have a sensor offset, which may create some background from the imaging conditions. So in this image, for example, we can see that it's a composite image of 3, and here we have the overlay. And so they are very well detected. And if we look here in the background at the intensity, what we can see is we have 105 in this image, 225. So here is quite high background. And here we have 143. It's also quite wide. And this is the reason why this is grayish, because we have a high background. So in here, in this image, we have the camera offset, and we also have mounting medium autofluorescence in here. And why do we have this camera offset? So it works a little bit different from a single point confocal. The camera's electronics cannot deal with 0 values. And that means that the camera manufacturers, they always add an offset. So we never start at 0 with a camera. Whereas in a single point confocal, we could have an image that is 0. So if you turn off your laser and you get an image, you will get very, very close to 0 with a single point confocal. But on the camera, you can't do that. You take one image with no laser, your value will be around 100, and that is called the camera offset. So to remove the camera offset and sample background from the images, if you have an image like this, where you have a mixture of camera offset and sample background, what you can do is that you can subtract the minimum intensity. So you can define an area here, look at the minimum intensity and subtract it from all the image. So after acquisition, that can be fixed. In Fiji, you can use the background subtraction, which is a rollable algorithm to remove and make this background a little bit darker. Okay, so this is all accepted, totally accepted. Of course, if you do some manipulations like this, you must describe it in the material method. But you can see in here after subtraction that we have a much more contrasted image in here where the background is darker. So this can be fixed after acquisition. If you only want to remove the camera offset, which is here, so what you do is you acquire an image with no illumination light. So you turn off the laser, get one image. They measure the value of the pixels that you have in this black image, and you will see that they will be 100. In some cameras, you can get something that is around 200. And then you subtract this value from the intensity of each pixel in the image, and this is the way to subtract the camera offset on a camera-based system. So what happens if we do not do that? Well, if you're extracting intensity information and you have dim samples, you're in trouble. Your intensities will be wrong. Let me have a look. So let's say that we want to compare two samples, A and B. Okay, and in one of our samples, we have the region of interest that the stuff we are interested in has an intensity of 2000. And then in the second sample, we have an intensity of 200. And this is quite dim. It's quite close to the camera offset, which is 100. Okay, can we say that sample A is 10 times brighter than sample B? No, we can't say that because we first need to subtract the background. So on the camera-based system, if you are comparing intensities and you have a bit dim sample, you must do background subtraction. So if we consider here, of course, if we do without background subtraction, we would come to 10. But this is the wrong value. If we first subtract the background, this is going to be 1,900, and here is going to be only 100. And therefore, the ratio is 19, So the difference between these two, sample A and sample B, is much higher than we think. Oops. And that is because we need to subtract the background, okay? And this is the correct value. So treat all images in the same way and report that you've done background subtraction in your articles. But remember that on the camera-based system, you should always, if you extract intensities from the images, you need to, and you have some quite dim samples, you absolutely must you must subtract the background. So now I spoke about background, and so I remind you, this is our little ball, and we have this interesting signal, and here we have the boring background, and we should cut the grass by lowering the background. But what is the noise then? Well, the noise is the fact that we have in the grass, they're not homogeneous. We have some long grass and some short grass, and it's a bit random. And that is the noise, okay? So please cut the ground. Let's have a look. How do we know that we have noise? This is a fixed sample, so nothing should move in the sample. Yeah, it's fixed, right? But if you have a look at this, now I have acquired a little time lapse of 3 images without any interval between them. So if I click on that, this is what I see. There's a lot of things that change from one image to the next, even though the sample is fixed. So the background and the signal are constant, but the noise is random. So this is what we are doing when we are using this little technique. We are visualizing the noise. The things that change between images is the noise. The stuff that is always the same in the background is going to be background. The things that are always the same in the brighter areas, this is signal. But the noise comes all over the image. So it comes everywhere, and it comes on top of the signal, and it comes on top of the background as well. It comes everywhere randomly from one image to another. And unfortunately, it hides dim signals. So you can see in here that it creates an uncertainty. If our scientific question requires us to accurately count the small dots and measure their surface, you can see that we are a bit unable to see where these dots start and end. Sometimes we even wonder if there is a dot or not, just because the noise is on top of the signal. So it creates an uncertainty. And again, it's always the same thing. Ask yourself, is this noise influencing my interpretation of the image? Is it going to change the way I count these dots if this is what I need to do or not? If it doesn't, you can just not care about this. But if it influences the result, then you have to eliminate the noise. So after doing changing the settings on the microscope, and then I will show you what you need to change to get to there, you can see that now this is also a little time lapse. There's very little things that change from one image to another. So we got rid of the noise. And what we can see now is here we had 2 dots. And this was absolutely impossible to see in this image, which was noisy. Okay, so if we remove the dots, the noise, we can then enjoy the resolution of the objective in this case. So the noise can come from different places as well, and it's important to know where it comes from so you can deal with it. So let's have a look at the sources of noise. So I've said that when the photons come into the detector, unfortunately, the detector or the sensor is not going to detect all of them, and that leads to the quantum efficiency. And then we create an electron, or we create a charge inside the sensor, and then we amplify this, we read the voltage, and then we have a conversion to a digital signal. And all this, and then we create a digital image for each of these pixels. So part of the noise is shot noise, and we're going to talk about this. Another part of the noise comes from dark noise, which comes from the amplification. And another part of the noise is the readout noise that comes from this process of amplifying, reading the voltage, and converting. Okay, so these 3 noises have different sources, and therefore we deal with them in a different way. So there's different solutions for them. And these, what I'm going to tell you now, is true for both detectors in single point confocal and cameras. So let's start with the dark noise. And the reason why we start with the dark noise is because we can't do anything about it. So this is created by the electronics in the sensor. And it's usually negligible, except if you have super dim samples. and you image very fast. So in general, the dark noise is negligible. And anyway, we can't do anything about it because we don't have any settings that will help us with the dark noise. In some cameras, we can add a cooling system to decrease the dark noise when we are really imaging very fast and very dim samples. And this is true for detectors and cameras. In general, the dark noise, we can ignore it. Now, the shot noise is very different. That we can do lots of things about. Light is a random process. So, photons are, it's a statistical process, basically, where the photons are along the wavelength. So we have, because it's a random process, there is an inherent noise that is created, and it is Poisson shape. So it has an even distribution as a Poisson shape. And this is an inherent noise because we are imaging light, and this noise is called the shot noise. This is not created by the sensor. It is only created because we are dealing with light, and that's a random process. So it can never be eliminated. As long as we're dealing with that, we will get shot noise. And it comes from the statistical, it's a statistical noise. But there's one thing that is good, is that the shot noise is the square root of the signal, okay? So that means that if we increase the signal, we're going to proportionally decrease the noise. So let's have a look at that. In this image of a nice beach, we have here very few photons coming to the camera. The image is very noisy, very grainy. We can see that. So we don't need to have a little time lapse here to see the noise. It's so strong that we see it straight away. In this image, it's a little bit less obvious, but there's more photons coming to the camera and we have a better definition. In this one, we have a lot of photons coming to the camera and we have a super definition. So what we have here is that the signal in this image, we can say, and it's random numbers, let's say that the signal here is 4, okay? The shot noise is going to be a square root of that, so 2. So the signal to noise ratio in this image is 4 divided by 2, 2. So we have 50% noise in this image, okay? 50% of what we're measuring is actually noise. Now, if we increase the signal here to 16, from 4 to 16, the shot noise is still a square root, so it's going to be 4, square root of 16. And therefore, the signal to noise ratio is going to be 4. Now we have 25% noise simply by improving the signal. And because the shot noise has a square root relationship with the signal, now we have 25% noise. We have improved our signal to noise ratio. And in this image where we have a very strong signal, the shot noise is only 55 compared to 3000 in the signal. And therefore the signal to noise ratio is going to be 55. We have 0.02% noise, so this is negligible. Okay, so one of the ways to deal with the shot noise is to increase the number of photons that participate to the image. So you can see the consequences of having a noisy image. In here, we can see the big stone, okay, but we have no clue about the clouds and we have no clue about the little stones on the beach. Whereas if we look in the the image that is with a high signal and a low signal, a high signal to noise ratio, we can see all the little details everywhere. So this is an advantage with the shot noise. We cannot eliminate the shot noise, but because it has a square root relationship with the signal, if we increase the signal, we actually decrease the proportion of the noise that comes into the image, and we increase the signal to noise ratio. So for the shot noise, we can do lots of things because there's a very strong influence of the software settings this time. So how can we decrease the contribution of shot noise? We need to increase the number of detected photons. And this, again, it's true for cameras and it's true for detectors as well. So how can we increase the number of detected photons? We can increase the illumination power. We can increase the exposure time. We can decrease the scan speed, so we must have longer pixel dwell time. It's the same thing as increasing the exposure time, basically. And we can open the pinhole if we're on a single point confocal. We can also match better the fluorophore and filters. if we start our experiment with a fluorophore that we only excite at 30% and we only collect 30% of its emission, we're clearly shooting ourselves in the foot. So if we match better fluorophores and filters, we're going to have a brighter sample and therefore a less noisy image. So we can also use brighter fluorophores. All this is about design of the sample, right? And this is at the acquisition time. And this is true for detectors and cameras. So there's a lot of things that we can do with shot noise, and this shot noise is basically the biggest part of noise in our images. Now, the last source of noise is the readout noise, and that can be also significant. So there's a strong influence of the software settings for the readout noise. It is linked to the speed of reading the electrons, amplifying them, and converting. So the faster we want to go, the more readout noise we are creating. So it's a balance again to be had there. So how can we decrease the readout noise contribution in our image? We need to either lower the amplification, because it's the amplification process here that creates this noise. So we can lower the amplification, or we can lower the speed of the readout. And on single point confocals, what can you do to decrease this source of noise? You can lower the detector gain. Do not push the detector gain too high on a single point confocal. So if you lower the detector gain, your image is because that creates noise. If you lower your detector gain, the image is going to be dimmer, and therefore you have to compensate this by increasing the illumination power, or maybe decreasing the scan speed, so longer pixel dwell time. You need to open the pinhole maybe, and of course you need to do your job with the sample. So do not push on the single point confocal, do not push the detector gain very high. It is better to increase the laser so that you do not create noise. On the camera-based system, we have something called the readout rate. And again, unfortunately, different software, they call it differently, but basically it's the speed. Sometimes they call it speed, high speed, low speed, something like this. So this readout rate, if you have something that allows you to choose, you need to use the slower speed, the slower maximum speed. So if you use the slower speed, unless you actually need a high speed. So try to just use the slower one. It doesn't mean it's slow, right? It's still a camera. So it's very fast. But you can see in here, you can have things like this readout rate in here. And then you have different settings. So have a look at the settings. But the one that actually allows you to go slower is the correct one. So in here, we can see this 200 megahertz and 550. It's how fast the camera empties the electron before it can image again. So as a default, use the slow speed, unless you need fast speed. Another way to reduce noise, so we have seen how we can increase the brightness of the image with to reduce the shot noise. Another way to reduce noise is averaging. So we have averaging in both camera systems and single point confocal, but there is less advantage in using averaging on the camera-based system. So sometimes in the software, you will not even get it. So in this image that is no average, not averaged at all, then you can see the image is grainy. It's like sand on the image. So this is a grainy image that has a lot of noise. And if we average 4 times, then we're going to get this type of image. So the difference between this and that is that we have less noise, but also it's a little bit blurrier, right? Because it's averaged. So if we average 2, it means we're reducing the noise by half. What do we do when we average? We can say we take 2 images, and from the 2 images, we're going to take the value from each pixel, and we're going to make an average. And what happens, because the noise is random, in the 2 images, the noise is going to go to different places, and therefore it will end up being half. But the fluorescence, the real fluorescence that is there, and the background. So the real fluorescence is going to be the same everywhere, and therefore it will stay at the same value when we average. So we end up getting rid only on the noise just because it's a random process. So the intensity of the signal and background stay the same. And but unfortunately, it takes double the time to image if we average 2, and 4 times if we average 4. Okay, and we get fuzzy edges because the noise has been there and was averaged, just all the edges are a little bit fuzzier. So it's a less accurate segmentation. And of course, they're more bleaching because we're taking longer to image. And there's more risk of sending the fluorophores to the dark state, especially on the single point confocal. So you should use frame averaging and not line averaging. So how much averaging should I use? How do we choose this? Well, just do this test. Acquire a 3-image time-lapse to estimate the percentage of noise. And ask yourself, does the noise that I'm seeing in this little time-lapse prevent me from reliably answering my scientific question? Is my interpretation of the image changing from one image to another? And then ask yourself also if you have tried somehow to reduce the shot noise and the readout noise, because that's quite easy to do. If you have, if the image, if your answer to the scientific question or to the way you interpret the image is not affected by the noise, just forget it. The images are noisy, fine. As long as it doesn't prevent you from answering your question, just leave it. If it prevents you, then you put 2x averaging and you test again to see, can I answer my scientific question reliably or not? If still you cannot, then you add some averaging. So if you can, do not use averaging. The images will always look nicer, but that's not what we're after, okay? And so this is true for detectors and cameras. So if we look about what we spoke about the contrast, we have signal to noise ratio and the signal to background ratio. So we know now that the signal is the intensity in the pixels of interest. The background is the intensity outside of the pixel of interest. And the noise comes all over randomly by single pixels that are brighter, basically. So if we look in here at the contrast, in the center here, we always have the same signal. So it's going to be 300 in this pixel in the center. And now we're going to have different types of noise. So we have the same background everywhere, but the noise is going to change from one image to the next. It's going to come randomly. And therefore, we have as we increase the amount of noise, so here we have plus minus 100, so we get a very low signal to noise ratio. And in this one, we get a good signal to noise ratio because we have little noise. So this is the way the noise can decrease your contrast because it falls everywhere. And so you're getting like all the background is also changing. So what is good enough? What are the good enough signal to noise and signal to background ratio? Again, this is whatever allows you to reliably answer your scientific question. If you're not after small differences, if you're not after fine readings of the image, you don't care, okay? This is the same for everything. It's the same for the optical resolution. It's the same for how you prepare a sample. It's the same for the digital resolution. If you have a very rough readout, you can get away with murder and do whatever you want. But as soon as your image, as your readout becomes like finer and you want to compare small things, then you have to be careful. So now I'm looking at my time. I'm good. So in conclusion, for this little lecture, we have background and signal that are located at stable places in the sample, and these are real fluorescence. So background is real fluorescence, it's just what we don't want, and signal is what we want. So noise, however, is very different. It looks like small dots that appear at random location and are different between different images. This is not real fluorescence. This is the intensity of the image is changing because of the basically the imaging process. Increasing the signal is a very efficient way to improve an image, but decreasing the background and the noise is often forgotten, but this is as efficient to improve an image as increasing the signal. what we are after is not a high signal. What we want is a high signal to noise ratio and high signal to background ratio. So we can work on the signal, but also work on the background and the noise. Don't forget that. The SNR, unfortunately, is often, the signal to noise ratio is often used wrongly for both SNR and SBR, but it's very difficult. It's very important to differentiate them and to know where your background comes from and to know where your noise comes from, because since we have different possible sources, we also have different solutions. So the background can come from the sample or it can come from the imaging solutions. And mostly it comes from the sample. And like, for example, mounting medium that is fluorescent or sample that are fluorescent, but it can also come from the camera and detector offset. So the camera offset is always there. We always have about 100 counts as a camera offset. And the noise is mostly shot noise and readout noise. It's actually mostly shot noise, but the readout noise, if you image fast, becomes significant as well. To decrease the shot noise, you need to increase the signal. You need to increase the number of detected photons, and that is done by choosing good fluorophores that work for your microscope, but also increasing the illumination and the exposure time. And to reduce the readout noise, simply use the lower gain in your detectors, and for a camera, use a slow readout rate. And then you have to compensate by increasing the signal with these two things. And then you can also use averaging to decrease the noise. So that doesn't work for background, right? It only works for noise. And you can also do some post-acquisition processing, and they are very efficient at removing noise, especially now that we have AI. There's a lot of tools to remove noise because since noise is always dot-like, it's 1 pixel at a time. So there are some very nice ways to post-acquisition remove the noise. So the best signal to noise and the best is the signal to noise. The best signal to noise ratio for you is the one that is required by your scientific question. So always design your thing backwards. What is it that I want? What are the worst images that I can acquire and still answer reliably my scientific question? That's what you're after. So what is your goal with acquiring this particular image? Again, if you are right now at this moment, you are making an overview to try to find the edges of your sample, you can have a super noisy image. It's fine, no problem. But if you want to publish an image in the front page of your favorite journal, just acquire a fantastic looking image, very, very bright, no noise, use your averaging, push the lasers, put the low gain and really acquire a beautiful image, because then your goal with that image is to make a beautiful image. But if you want to get data for image analysis, acquire an image that allows you to reliably answer your question. This is all we want. And it doesn't matter if it looks ugly. It's actually very often an advantage if it looks ugly, because you spend less time. Okay? So I would like to know if there are questions about all this.
I have two questions. The first is there any, apart from perhaps more bleaching with longer dwell time, is there any fundamental difference between doing 2 times averaging and doubling the dwell time in confocal? Is there any situation where you should choose one or the other?
Yes. So when you do averaging, you can do averaging in different ways. You could average by taking one image first and then a second image and then averaging. Or you can average by doing one line and then a second line and then averaging. And you do the same thing for each line in the sample. Or you could decide to integrate longer with the dwell time, right?
Yeah.
So the difference is, do you give a chance to the fluorophores so the difference is the risk of sending the fluorophores into the dark state, because on a single point confocal we have such high power that we have a lot of cycles of ground state, excited state, ground state, excited state. And the more cycles we have statistically, we have a higher chance of the fluorophores going into the dark state, in which case you are depleting the fluorophore in your sample.
Yeah.
You cannot use. And so it goes against you, because if you're depleting the fluorophores, the sample becomes dimmer.
Yeah.
Less photons, more noise. So it is always better to image one image after the next. If you cannot, you do one line average. If you cannot, you go slower.
Okay.
But sometimes if we image, so it's a bit the wrong setting, but if you would want to image a live sample in with a single point confocal, and if it's a sample that moves fast, so clearly it's not the ideal settings. But if this is the case that you want to image a sample that moves fast, sometimes you don't have much choice. And you have to image faster, otherwise the things, you don't have time to image the whole image, the sample will move. So then you maybe want to use the line average.
Okay. The last question is about the gain. Is if this is only about the amplification and we don't care about the beautiful images, as long as we have enough bit depth, then I guess it doesn't matter to increase the gain. It's still the amount of photons that hits the detector. We're only or
So when you
should
are
I be touching
increasing,
this at all?
the problem is when you, if you use high gain and low laser, you
Yeah.
start with very few photons and you amplify them.
Yeah.
And so you amplify them a lot. And so that means that the contribution of the noise that comes from the amplification, so
Yeah.
the equivalent of the readout noise for a detector, will be significant because we start with high shot noise because we have few photons.
Yeah.
And then we amplify, we add a lot of readout noise as well. So it's much better to increase the laser and have a lower gain.
Yeah.
But of course, there's a sweet spot there.
Yeah.
And because you don't want to put too many photons if we bleach, for example, if we do Z stack, we want to be a bit conservative with the laser. So there's a sweet spot between having not too little gain
Yeah.
and having tons of laser and the opposite.
Yeah.
So in general, if you have a fixed sample and you have no problem with bleaching, it's better to increase the laser than increasing the gain.
Okay. Thank you.
And I must say, it depends also, it's very variable from one detector to another,
Yeah.
where you're going to start getting the noise. So
Yeah.
gas detectors, for example, they start making noise, they're very sensitive, but they start making noise very quickly when you go
Yeah.
up.
I
And
mean,
then a normal PMT is a little bit more resistant, and you can put it halfway through the slider and without creating noise. So you just give a try.
yeah. I mean, my question point was more if I ever should increase the game, because as long as you have enough bit depth, it doesn't matter if it's like if one photon is counted as 2 or as 20 photons. I guess it's still a certain amount of photons that hit the detector. So how much is amplified is more about how we fill out the pixel range. Or
Well, no, because you are also hiding with the noise. You don't want to
okay.
have noisy images. I mean, even if you have if you put a low laser and high gain, and you anyway have lots of electrons, so you have a good value of intensity at the end. But if it's full of noise, it will prevent you from analyzing.
Yeah.
Are there more questions? Yes, Ellie?
And sorry, I wanted to ask what the offset zero value means. The offset can go to negative as well, because I don't remember.
Yeah. So on older systems, yours is what is your system? I forgot.
LSM 980.
980. So this is a new system, and therefore you do not have any offset, or do you?
I can manipulate it from the software.
Okay, you can change the offset there. So in general, okay, I'm not super familiar with the Zeiss system, but I think that in general nowadays on the newer systems, there's a new way to calculate the offset, let's say, that has been implemented some years ago, where it's automatically deducted from the signal, and therefore you just shouldn't touch it. But until maybe the systems that were bought produced like 10 years ago or something like this, so it's not that far away. you would have something with the offset that you would have to change. And for that, you put the color mask blue and red, and then you should have no blue in the image. No red, of course, no saturation, but no blue. Victoria?
Yes, I have a question about the um about increasing trying to increase the signal. You mentioned increasing the laser power, but how do you balance that with increasing the exposure time?
Yeah, so you're on a camera-based system, or?
Yes.
Yeah, so it's the laser power and the camera exposure. You want to try, and if you have a big sample, you want to image as fast as possible. I am not 100% sure, but I think that increasing the laser power versus increasing the exposure time, it's about the total, basically the total light exposure is going to be the same on the camera-based system because the whole field is illuminated anyway. So that means that there will not be a big difference between increasing the laser with a short exposure time or lowering the laser with a high exposure time. For a live sample, for example, I think that the cytotoxicity is going to be the same. But if you have a big sample, clearly you want to keep the exposure time low so that you image faster. So this is the way, I think that I have read this before, that if you increase if you have a high laser power and a low exposure time, or the opposite, the total exposure to light is the same, and therefore the result in phototoxicity, photobleaching is the same.
Okay, thank you.
You're welcome. Any more questions? Okay, but if not, we are now going to go for a little break. So we come back at 45 past, and I see you in a workshop. So